Hello, my name is Andrea Lazcano, and I will present an overview of my project, performed in a collaboration between Delft University, Toyota Motor Europe, and Cambridge University. The project is an MPC-based haptic shared steering system that makes use of driver modeling in order to foster collaboration and reduce driver-assist conflicts. We will start with an introduction of the current situation of vehicle control. Afterwards, I will recap the two main pillars of this new assist system, which are driver modeling and model predictive control, combined within the haptic shared control framework. Later, the results of the driving simulator experiments will be presented, and finally, the main conclusions and future steps are outlined. Let's start with some background regarding the automotive sector. The different projections towards the deployment of fully autonomous vehicles predict several decades of progressive increase of automation until self-driving cars become widespread. Until then, automobiles with partial level of automation provide intermediate scenarios from basic driving aids to effective shared control between man and machine. In particular, in haptic shared control, the driving task is performed simultaneously by the user and the controller, combining the best qualities of each of them. In addition, in this strategy, continuous collaboration is present through the exchange of feedback. And this is why we consider haptic shared control to be the most suitable approach. Now, the big picture is advanced driver assistance systems are meant to increase comfort and safety while driving, but they often perform badly because they tend to prioritize an unnatural path tracking performance because they do not consider the human factor due to this complexity. But this change of concept is fundamental in order to increase user acceptance. Therefore, intelligent systems must take into account the closed-loop human-machine interaction in order to develop collaborative controllers. Therefore, a novel concept of the proposed controller is that it contains an extensive driver model. First of all, driver modeling allows for a subjective-objective interpretation of steering feel. Secondly, we can use it to understand the closed-loop interaction, for which we define the sensory organs, the cognitive behavior, and the neuromuscular dynamics in the next slides. And with this driver model, we aim to realistically illustrate the human behavior. First, the cognitive model. Although haptic shared control can lead to less steering activity and increased safety, drivers sometimes resist the assist system due to, for instance, different driving control strategies. Therefore, a good model becomes essential in order to reduce the intrusiveness of current ADAS. The central nervous system is composed by the brain and the spinal cord, and its main function is to send control signals to the NMS. These commands, alpha and gamma, are calculated through a control strategy, the LQR, based on the desired states XKF. This is combined with a common filter used to reduce noise coming from the brain and the sensory organs. And at the same time, this requires an accurate internal mental model, which is a virtual representation that the driver has of their own dynamics interacting with the steering vehicle plant and the controller. And this image can be varied in complexity to capture different levels of driving skill. Moreover, the use of haptic shared control allows for the exploitation of the NMS, which is highly adaptive and fast. This is why a detailed representation of the muscle dynamics is essential. The NMS is composed by the reflex action of the muscle spindles and a linearized heel muscle model, including the activation dynamics. These elements are required to model the coactivation mechanism, and this coactivation is affected both consciously by alpha signals coming from the brain and unconsciously by alpha R signals. The latter is associated with gamma signals, which can be linked to an inaccurate internal mental model or the rejection of disturbances, which may be perceived negatively by the driver. Therefore, the reflex loop allows us to link driver acceptance to the neuromuscular point of view. We have just looked deeper into the cognitive and neuromuscular system. Lastly, the steering vehicle plant can be varied in complexity, and the sensory organs, such as visual or proprioceptive, characterize the driver limitations in the perception. Now, we have all the elements of a complete driver model. The second key element is the controller. We calculate the optimal human-like assist through model predictive control. And with this strategy, we can predict the behavior in the future of the car, but also the driver, in order to optimize the provided feedback guidance and reduce conflicts with the driver. And this optimization is performed within a finite time window or prediction horizon, NP, and this problem is iteratively solved to minimize a cost function subject to constraints. Feedback control is introduced by applying only the first element of the calculated control input sequence, UK. And this approach makes the model robust against disturbances. Moreover, it can be implemented in real time, making it possible to integrate the advanced driver model in the loop. And this is done through a cost function that minimizes the tracking error and fosters collaboration. Driver discomfort is also tackled through the minimization of the muscle spindle torque. But these two objectives can be competing, performance versus driver comfort. So we design a dynamic objective that better adapts to the different driver needs. The adaptive level of authority is a feature that most research fails to design in a natural way. But with this approach, we can truly design a shared control system. As you can see, the model has a high level of complexity, but in short, an advanced driver model was integrated into the assist system with the aim to represent human behavior and predict subjective assessment of the feedback torque within our haptic control framework. Now, we have performed experiments in a driving simulator to assess the performance, collaborative behavior, and subjective acceptance of the proposed controllers against a commercial benchmark, both objectively and subjectively. All three controllers provide feedback torque to the driver to track the center of the path. And in the figure, you can see an overview of the driving simulator setup, with the human in the loop interacting with the controller. The driving simulator scenario consisted of a 5-kilometer long road with straight and sinusoidal segments in order to ensure repeatability of the maneuvers. Moreover, the only task of the driver was to control the lateral motion of the vehicle, with the speed set to 100 kilometers per hour by an ACC. Finally, the lane width was set to 5 meters and no lane markings were present in order to assess the behavior of the proposed controller subject to intra-driver variability and different human perceptions. This is a summary of the subjective evaluations of the 19 participants. From the responses, we can see that 80% chose the MPC mode 2 in pink as the best. And we can also see that the MPC modes in pink and yellow consistently outperform the commercial system shown in blue as baseline on overall steering effort, path tracking performance, collaborative behavior, smooth control, and feeling of being in control. This last one is graded lower in general because the level of control authority is partially given to the assist system, but this is not necessarily seen as negatively as long as the assist is collaborative. In general, the presence of driver-assist conflicts can make the perception of the controller being heavier than desired, as well as having a lower collaborative behavior in the case of the baseline. We can also see from recorded simulator data that the MPC is in phase with the driver inputs. So the MPC controller actively cooperates with the driver and minimizes conflicts, which result in improved path tracking performance. In the case of the baseline, some of the torque conflicts may result in a more intrusive guidance. Now, objectively, the tracking performance is assessed based on the RMSE of the lateral error, where there is an improvement of about 35%. And objectively, the collaborative behavior of the MPC controller in mode 2 increases by 60% with respect to the baseline. In other words, the intuitive continuous guidance of the MPC modes make an efficient use of the torque feedback in order to achieve a better symbiosis with the driver. Moreover, the proposed MPC controller significantly decreased the overall driver steering effort and level of being in control and level of control authority by 50%, in agreement with the subjective evaluation. Lastly, for the steering reversal rates, which is a measure of the workload of the driver and the smoothness of the control, the average improvement is of about 30%. To conclude, we have presented an optimal torque control law to foster haptic guidance, continuous cooperation, and the reduction of conflicts between the driver and the proposed controller. For this purpose, an MPC controller integrates an advanced driver model, which plays an essential role. The predictive driver behavior enables the MPC to provide a pleasant driver experience by keeping smooth driver in the loop dynamics. Moreover, the MPC controller allows for dynamic allocation of the control authority, which fosters symbiotic driving. Future work involves testing the controller in different scenarios, as well as evaluating it in a test vehicle. With this project, my aim is to contribute to the development of human-centric ADAS. Thank you.